Hi students, let's talk about Hooke's law for a little bit. We're going to do a practice problem in just a moment about Hooke's law. So what is it? Hooke's law, basically it shows the relationship between how much a spring, here's a spring, can be compressed or stretched out, right? This one doesn't stretch so much, but by how much force is applied and then also the stiffness of the spring. Okay, so the amount that it will be compressed or stretched out is determined by the force that's applied to it and the stiffness of the spring. And it's a simple equation. It just says that the elastic or restoring force is equal to minus kx, right? K is the spring constant and x is the amount that it's stretched or compressed. So I have another little one here. And so this one, it's pretty easy to stretch that out. And this one here, even though it's smaller diameter, it's actually a little bit stiffer, right? It has a higher spring constant and it requires a bigger force to stretch out that spring, right? This one can compress and it can stretch a little bit, but the relationship is found by Hooke's law. So here's the practice problem that we're going to do. You can pause it to read it, and then I'll show you how to complete it.
Okay, so we've seen what the sample problem reads. It says we need to find what the spring's displacement is when we have a mass of 3 kilograms and it's attached to a spring scale, and the spring constant is 36 newtons per meter. So the way that we'll do this problem then is let's just list everything like we normally would. So the mass will be our 3 kilograms, and we have a spring constant. We'll use little k for spring constant, 36 newtons per meter, and then we want to find our displacement, which we'll just call x. So here's the diagram that I'm going to draw for this. So we've got some support and we have our spring, and there's a mass that's attached to the spring, and we'll call this this is like our before side over here. And then we've got our same support. And now what happens is once we let go, then the mass is allowed to stretch down. So we started at this distance here, and now we're going to this distance here. And this is going to be what we're trying to find, is how much did it actually stretch from this position, and then we let go, and it stretched all the way down to here. Okay, now when we get to this bottom point, we don't want it to be oscillating anymore, so we want it to be at rest. So if the mass is at rest, then we're in equilibrium. And if we're in equilibrium, then we have a Newton's first law condition. And let me just finish this, and right here's my after picture. So what we'll do then is we'll just draw over here a dot to represent the mass. And just like we've done with forces, we know that gravity, our force of gravity, is pulling downward. And we know over here, upward, this force, this upward force, is the spring pulling back up. And so what we would say is that this is the elastic force. I'm just going to put Fe for elastic force. And it's really just the y-axis, right? If I were to just continue this, that's my y-axis here. And then I would have my x-axis here. There's nothing on the x-axis for us to worry about for this problem. So I just have this force that I'll color in and this force here that we'll color in. So if I wanted to, just like we've done in the past, then what I would do is I would sum up all of the forces. In this case, there's only the x-axis. I've got my elastic force upward. I've got gravity pulling us downward. And we'll set that equal to 0 because we're in equilibrium. Only looking at this part here, you can see that the elastic force has to be the same as our force of gravity. And what is Fg always equal to? Mg. So that means that our elastic force in this case equals mg. So this will be important in just a minute, the fact that our elastic force is the same as our weight. So we need to figure out what x is equal to. Well, where do we find x? We find it in Hooke's law. So Hooke's law says that our elastic force equals minus kx. So let's just talk about this very briefly for a second here. This minus sign right here, this means that displacement is opposite direction of the force. So if I have a spring, like we have up here in our example, if we take a look at the after picture here, you can see that our displacement went this way, downward, but the force is pulling back upward. The elastic force is pulling back upward. And so that's where that minus sign comes in. It just tells us that they're in opposite directions. So then what we can do is, I'm just going to rewrite it. We've got our elastic force equals minus kx, and I have to solve this for x. So x equals minus Fe, our elastic force, over k. And what did we just find out? Well, we found out before that our elastic force equals mg. So I can just do a little substitution and throw that in over here. So then this would be rewritten as minus mg over k. So the equation that we get for this then is x equals minus mg over k. Not too bad. We've done harder problems, I think, in the past. And that's it. That's how we would solve this problem. So let's put the numbers in now. So we've got minus our 3 kilograms times g, 9.81 meters per second squared, divided by our spring constant, 36 newtons per meter. We put all this into the calculator and we get minus 0.82 meters. And that's the answer for our practice problem. And you'll see that this is actually one of the problems that is assigned for your work to do. So there you go. Fairly straightforward Hooke's law problem. Give the rest of those a try and let me know if you have any questions.